You can see the slides. Okay. So let's continue with the first type of deposition. We call it PVD, physical vapor deposition. And yesterday we have discussed that for PVD we have evaporation and sputtering, and even for evaporation we have thermal evaporation and electron beam evaporation. So this is evaporation in general. So we've covered some basics of the evaporation process. Hold on, let me. Right, some basic of the evaporation process. So on this page, you can see important components of an evaporation process. So we have a chamber evacuated usually down to about -5 torr. So that's what we call the base pressure. And typically when we run the evaporation process, we turn on the current through resistive heating. We're going to see the video on YouTube today. The pressure is going to go up a little bit up to maybe 10-3, and then you start to have the evaporation of your precursor material to the substrate. So we have a chamber, we have a distance of separation between your source and your substrate. So the substrate can be anything, it can be wafers, can be glass, can be other substrate. It can in fact be layers on substrate. So you may have a range of different substrate for the deposition because it's not in contact with the source anyway, right? So you need to have a sufficient vacuum level so that the mean free path is enough. So you need to have. Oh, you cannot see the slides. The rest, can you see the slides? Or it's just Ain? The rest can see. Ain, maybe if you still couldn't see, you try to leave the session and join again. Okay, because others can see. You join again. Okay, try again. So these are the important parameters, if you like, for an evaporation process. So evaporation is a line of sight deposition. That means you need to have your sample aligned properly in a straight line in comparison to your source material. So you cannot put the sample away from the center of the deposition line. If you put away, you may end up having nothing on the sample. Right, this is again the same thing. So arrival of flux of the atom. So basically, number of atoms per area time that you have, right? So the flux here is made of your precursor material. So it can be metals or it can be some other stuff. But typically, when we talk about evaporation, we normally use metals, but not necessarily. So during my PhD last time, I used electron beam evaporation to do the deposition process. And I did the deposition of silicon film. So that's about 10 micron thick on glass substrate. So that's done on e-beam evaporation system. So it can do on silicon as well. But the common precursor materials used for evaporation are usually metals. Right, the rate of film growth is strong function of the source temperature. So you normally have source temperature, and then as an option, depends on the system, you may also have substrate temperature for the for your substrate here. So substrate temperature or source temperature means you can actually regulate, or you can control the temperature of the source or of the substrate. So in this case, the source is mainly controlled by the current passing through the source in order to initiate the evaporation. But at the same time, you can actually vary the substrate temperature of your silicon or of your glass, right? Or you may even leave it at room temperature. Okay, it can also be at room temperature, or you can also increase maybe at T 200 degrees C or 300 degrees C, or in fact higher. And this substrate temperature will normally affect the properties of the sample, right? So it could be your structural properties, morphological properties, optical properties, electrical properties of the sample that you want to deposit. So mean free path, we discussed a little bit yesterday, mean free path, what we call lambda. So it's actually an average distance which the gas molecule travels before collision. So we have discussed yesterday about this flow, right? Where you have your solid source. Say if you want to evaporate aluminium as your metal contact, so you normally cut the aluminium wires into small chunks or small pieces so that you increase the surface area for evaporation. And then the moment you have enough vacuum level, you turn on the current, initiate the resistive heating process, then you will then evaporate the solid material into gas phase, and then the gas needs to travel through a distance to get from the source to the substrate in order to be deposited. So the distance that they have to travel have to exceed the separation distance between the source and the substrate. If the journey that they will go through, they go through is not exceeding the distance between source and the substrate, so they won't end up on the substrate. So you need to make sure that the journey or the distance gone through by the gas phase is more than the separation distance. And this is what mean free path essentially means. So average distance which the gas molecule travels before collision. Kalau you ada collision along the way, so the gas phase is going to be gone, so the gas precursor is be gone, so you won't have your film deposited on the substrate. Okay, so the equation is given there. Okay, so the mean free path is dependent on the pressure level. So the lower the pressure level, the longer the mean free path will be, right? So look at the table below. So for example, if you if you evacuate your chamber down to about 10-2, so your gas phase can only travel up to 0.5 cm. 0.5 cm before the next collision, right? Before the next collision. That means we assume that for this deposition, the moment it experiences a collision, that is going to be gone, and you're not going to have your film deposited on the substrate. So if you use your vacuum level only down to 10-2, so that means your particle can only travel, your precursor can only travel like 0.5. So 0.5 is super small, right? So it's not even this thick, right? 0.5 cm is too small, and well, it's not practical, of course. So that corresponds to 90,000 if you want to translate into the number of collisions per second. So that's like 90,000 collisions per second. Okay. So on the other hand, if you reduce vacuum slightly more down to 10-4, for example, now the gas phase or the precursor material can travel to 51 cm. So 51 cm is like your baris panjang plus baris pendek, that's 45 cm. So slightly more than that, right? So that's probably enough, but usually we'll normally prepare the system to be having more than that, right? But 50 is typically enough depending on the system that you have, the chamber size and stuff. So that corresponds to about 900 collisions per second. So if you have lower vacuum levels, so that translates into lower collisions per second because you have less particles, less residues, less contaminants left inside the chamber at that particular vacuum pressure. If you reduce the vacuum level further, down to -5. This is the typical base pressure that we use in order to prepare our film deposition system. So this is the standard one. I put asterisk there. So your mean free path increases up to 510 cm. So is this enough? Do you think this is enough for a deposition to take place? 510 cm. It's good, huh? Do you think it's enough or you need more? Okay, anyone? Fix that. 510 cm. That's what, 5.1 meters? 5.1, that's like my height times 3. So more or less. Okay, so that's more than enough. So you won't have a chamber that long. So maybe ceiling via height code is slightly more. So that's usually more than enough. So we normally do more than enough in order to ensure the deposition takes place, right? So 510 cm, so that corresponds to only about 90 collisions per second. And that is more than enough to ensure that your film is deposited on the substrate. So if I can relate this to the chamber just now that we've discussed on the previous page. So for example, if you have your source here, maybe you have aluminum here to be melted. And this is your, for example, if you want to deposit your aluminum on silicon wafer, and say the deposition, the separation distance is perhaps around 40 cm, right? Depending on the chamber size. Some are bigger than the others. If you assume it's 40 cm, this 510 cm is more than enough for them to travel. So that's like 510 cm, right? 510. So the distance that your particles can survive is way longer than the separation distance between your source and the substrate. Okay, so that means along the way, the precursor is going to experience more or less 90 collisions per second while traveling from there to there, more or less. Perhaps less than that because the distance, the separation distance is only like 40 cm. So that's normally enough for evaporation system. Some can even go down to a lower vacuum level. So that means if you go to 10-7, for example, for your mean free path, so your particles can travel up to 51,000 cm. That's like 51,000 cm. Okay, so kalau you convert into meters, so that's about 510 meters long, very long. Okay, 510 meters long. You don't have to, but some system really runs down to this level. Okay. So last time when I did my PhD, the system base pressure was maintained at 10-7. So for electron beam evaporation system. So that means if you see the corresponding collision per second, so that's like 0.9 collision, not even a collision, not even one collision per second between molecules. So that's very, very low and very, very good. So of course, the lower you go is the better for the system because you make sure that your space is super clean. But then you need to have a good vacuum pump, for example, a turbomolecular pump. If you want to run down to -7, so you need this pump in order to maintain the chamber pressure, right? So you need a more sophisticated pump if you want to maintain a lower pressure. So this is what I meant by explaining the distance away from the center, because it's a line of sight deposition. It's a point source. So for example, if you place your aluminum here to be melted, so you want to place your substrate right on top. You want to place your silicon down here, for example. And you don't want to place your wafer here. Right? Center is the best because it's a line of sight deposition. If you place it slightly off the center, it's still okay. If it's too much away from the center, it's not okay, right? So you'll probably experience a thinner aluminum on your sample that's away from the center, and you might experience thicker aluminium deposited on the center right on the line of sight. So film deposition is not uniform throughout the wafer due to difference between the distance of source and the wafer. So separation distance is one thing, and the effective distance here and here are different as well. You can calculate that by knowing the angle. So angle which the flux arrive at the wafer surface is different. So you end up having different thicknesses of your aluminium on both wafers at the center and at the edge of the holder, substrate holder or wafer holder. All right, advantages and disadvantages. Problems: difficult to get thickness uniformity over large wafers. So it's a lot harder to control uniformity on the large wafers. So just imagine if you're in a fab, then your fab is running 8-inch, so 200 mm, and your next fab is running 12-inch. So your other fab is running 18-inch. So it's harder to control uniformity across the wafer if your wafer is bigger and bigger, right? So that means if you use a line of sight deposition process, you need to make sure that, well, the wafer is already big enough, even though it is placed at the center. So you might have multiple sources to ensure uniform deposition over the whole big wafers across a batch, because the deposition is not done wafer by wafer, it's done in a batch. So that means you may have like a couple of wafers in a batch of deposition. So if considering each wafer is like 18-inch, so you have like perhaps 10 of them, and they are placed in a batch, and then you want to run the deposition. Just imagine what we call the pressure that you put on the system to deliver uniform deposition. Multiple components require multiple sources. So we discussed this one yesterday when we discussed about cadmium telluride, cadmium sulfide, for example, or CZTS, right? So each, if you look at this CZTS, for example, each element is melted at different temperatures, and they have different vapor pressure as well. So you might want to check this. They have different vapor pressure as well. So if you use a single source, for example, if you have CZTS as a single source to be evaporated, then you will probably see whatever you have on the substrate will not be stoichiometric in nature. So you won't have like exact proportion of CZTS as you intended, because the vapor pressures and the melting points of each element is different for you to do a single source deposition. Difficult to evaporate high melting point sources. Typically, we use evaporation for low melting point. Well, when I say low melting point, usually when you want to evaporate, we normally evaporate materials with a temperature melting point of lower than 1000. Well, it's not a golden rule, but this is how it's typically done. So if you want to evaporate aluminium, for example, aluminium melting point is like 600 plus, silver is 900 plus. But if you want to go for titanium, palladium, and those silicon nitride, for example, it's going to be very hard for you to evaporate on evaporation system, to deposit on evaporation system. So that's why we have another PVD system or another process like sputtering and so on in order to do the job, typically for dielectric materials or materials or metals with higher melting points. So low throughput, it can be low throughput due to UHV requirements. So if you're talking about below 10-7, then it's going to be at a very low vacuum level, or we call it UHV. So that takes quite some time in order to be evacuated, in order to prepare the chamber. But usually when you need a system with UHV, nanti I'll try to find a source to share with you. Normally kalau kita Ada any one of you yang pernah run evaporation system dekat no lab so that you can you have a better picture. Anyone pernah evaporate? Siapa? Ilham pernah guna? Ilham?
Tak pernah.
Pernah. Anyone? Inas pernah guna? FYP ke dulu tak pernah guna lah? Tak pernah. Anyone pernah guna evaporation? Naim pernah pakai Naim? No, no one. Apa Naim tak pernah? Nabila? Oh, semua tak pernah Tak ada yang buat metal deposition lah. Mungkin it happens to be no project in applied physics using thermal evaporation. Apa ni? Yeah, so low throughput. Typically, when we use a system with UHV, nanti kita akan tengok video. You're gonna have a chamber like that, but for you to insert sample, katalah you dah habis deposition, kita tak nampak lagi gambaran tu. You need to remove the chamber, right? You need to remove the chamber so that you can take out your sample for next processing. To be able to remove the sample from the chamber, you need to vent the chamber. Right? You need to vent. Vent means V-E-N-T. Vent means you increase the pressure from whatever your current pressure is, for example, 10-7 ke -6 ke, up to atmospheric pressure. So that's called venting process. You increase balik pressure dia supaya the pressure inside the chamber is comparable to the atmospheric pressure. Barulah you boleh angkat. Kalau dalam tu masih vacuum, macam mana nak tarik kan? It's going to be very hard for you to leave the chamber because it's vacuum inside. Susah nak tarik. Kan? Dia sedut kan? So you need to vent the chamber up to atmospheric pressure, then only you will just leave it simply to be able to remove the sample. But when you vent the chamber so that the pressure inside is equal to atmospheric pressure, bila you angkat, it's going to contaminate the chamber because you have like particles going into the chamber for your next job. Maksudnya you nak buat next deposition, you still have to close it, evacuate again from the atmospheric pressure down to about -7 so that you have a stable baseline or base pressure, baru you will start the deposition. But this process takes time, so that's why it's called low throughput, because you have to evacuate, vent, evacuate, vent, evacuate, vent from batch to the next batch to the next batch. So in order to eliminate this problem, people introduce load lock. Mungkin tak nampak, nanti saya try cari video to show you on YouTube maybe. Load lock. So maksudnya you punya kalau you pakai load lock, you don't have to vent the whole chamber, but you're gonna have like a channel which you can remove the sample, but the channel you ada chamber macam ni. Itulah ni UV chamber kan. UV chamber. So this is like at vacuum 10-7 maybe. Kalau tidak kita nak kena remove ni baru angkat sample. Remove sample. You have to vent first. So instead of venting, so people invented load lock. Load lock ni is a channel for you to remove your sample macam terus ada laluan lah, laluan. So what you have to do is the pressure in the load lock has to be at the equal level with the vacuum pressure. So that means this one is -7. So this load lock has to be evacuated at -7 as well. Then there are the valve in between. Ada penutup in between. So you open the valve when the pressure of both match. Then you buka sini, you ada robot arm akan ambil sampel. They shut off the valve. So dia tutup. So this guy maintains at 10-7. But this one, the load lock, sample dah ada kat sini sekarang, kat dalam load lock, so it's no longer here. This one is maintained at -7. So you can just vent the load lock. So this guy is not disturbed at all. It maintains at 10-7, so you won't have any particle contamination problem and no throughput problem, right? So load lock ni just a small channel aja. So you just have to Dia ada opening kat sini, you can remove a sample from here. But to be able to get a sample from the load lock, you have to vent the load lock. Tapi load lock kecil ya, so it's a lot faster to vent load lock than venting your whole chamber here because the size is way bigger. So you use load lock, vent load lock, then bila dia dah vented, so this guy is now equal to atmospheric pressure, you can open, remove your sample, close it back, or put your next sample, evacuate this guy down to -7. Then when this guy pressure matches this guy's pressure, you open the valve here, put in the sample, close the valve, do the processing, then remove bila siap. Done. So load lock is an invention. It's a good invention to eliminate this problem. Okay. So tapi kita punya system dalam lab tak ada load lock. So when you don't have load lock, you have to go through the process of venting the chamber from your base pressure, say -5, -7, back to atmospheric pressure. Remove the chamber, leave the chamber, remove the sample, put in new sample, close it back, vacuum it back down to -5, -7, do your processing. So it's gonna introduce potential contamination into the chamber every single time you open, right? And this is not tolerable for mass production. Untuk lab okay lah. Kalau mass production, this is big no-no because you have to repeat unnecessary process. So might as well you have a load lock and do your load lock properly. So that's what it means by this point. Post-step coverage, particularly because the nature is of line of sight deposition. So uniformity has to be guaranteed. So you might use multiple sources as well, and each source has to be uniform in nature so that you can ensure uniform deposition, uniform film quality on your substrate. Advantages, little damage to wafer. It's just a deposition process, by the way. Deposited films are usually very pure due to UHV, particularly if you use UHV, 7 and below. So your film is more pure, less contaminants, less impurities, because you vacuum it down to a very low level, but then at the expense of the throughput, perhaps, and you know, higher cost due to high cost of vacuum system. Electron beam based probes are available for analysis of surface structure during growth. You can also do film analysis during the growth process. So as you do the deposition, you can have a system where you can monitor the evolution of the film properties as the deposition goes on. Selanjutnya kita bila dah siap proses baru kita ambil sample and do the accessory characterization. But this one you can do real time characterization. Cumanya dia lagi mahal lah. Right? So yeah, step coverage. So if you have features, just like what we discussed on the shadowing effect during ion implantation. So this is a similar problem. It's also called shadowing effect. Cumanya now is due to the features, same features, during film deposition instead of ion implantation. So it's also called shadowing effect. It's due to the presence of features. So these features, you are on the wafer, so they will block certain areas or it will shade certain areas from being deposited. So as a result, you may not have certain areas covered by your deposited layer because of unidirectional nature. So kalau you ada problem ni, how do you think you can solve the problem? You have the features on your wafer. So let's discuss. You have some features on the wafer, and then you are running evaporation process, which you know it's line of sight deposition, unidirectional. Tapi you cannot avoid having features on your wafer. So what would you do to ensure a more uniform deposition? What would you do? Aniza, what would you do to ensure a more uniform deposition on your wafers? Anyone? Come on. Bagi idea sikit. Naim. Siapa Naim? How do you ensure you are, for example, if you are a process engineer for this process, film deposition, what would you do? Anyone? Any idea? Please type as well, chat box. How would you do? Hazika? Any ideas? Yes, good one. Can the sample be rotated? Yes, we can rotate the sample. So you are the batch, you are the sample holder yang besar tu. So you can actually rotate the sample holder lah, sample holder. If you rotate, you will improve the uniformity of the deposition. So maksudnya sample tu is rotated and it gets to experience multiple direction of deposition lah. So that will actually improve the uniformity of the deposition, right? So it can be by rotation, sample rotation. Okay, a vacuum requirement. This is what we discussed before. Typical system, you need a vacuum pump to evacuate the chamber down to -5, -6, -7, depending on what you need for your process. So cooling water, particularly if you have substrate temperature. So the moment you have substrate temperature, you're gonna use some heater to do the job. So you need some cooling as well because you don't want a system to overheat due to excessive heating and uncontrolled heating. So you can also use a mechanical shutter. So shutter too is usually it's usually here. So this is your chamber. So this is your source, aluminium, for example. So katalah you punya silicon kat sini. Silicon wafer. So before you actually start deposition on your sample, we normally have a shutter to block the deposition. It's usually mounted to the side of the wall of the shutter. So normally bila kita start deposition from the bottom, then kita akan close shutter first and let it run first. Let it run for a few seconds perhaps to do some cleaning. Then after some time, when the plasma is stable, when the deposition evaporation is stable, then you will open the shutter. So dia akan ada line of sight deposition straight to the sample. Okay, you will open the shutter and you will monitor the deposition rate on the system. Just like what you do on your sputtering process dalam lab. Kalau you pernah buat sputtering, then pretty much that's what it looks like, right? You open and then you start monitoring your deposition rate and stuff like that, and your actual thickness of the layer starts to grow, and you'll see that your thickness develops over time. So when we talk about evaporation, we have two systems. We have thermal evaporation, or we call resistive heating, and another system is called e-beam evaporation. Okay. So this is how it looks like. This is not our lab system, bukan kita punya lab. Ni Google punya gambar. Lab punya is on the something like on the video that I attached on the slide, on the next slide, I think. So it looks like this. You have a chamber of that big. I think this one is easily 60 cm maybe. By the look, I don't know the exact distance. So I think that's like 2 pembaris panjang kot at least. So this is the glass window that you can see. So you can actually see what's happening inside during the growth process. So this is what you see. Okay, this is what you see during the evaporation process. So this is where you play your sample, maybe wafers, right? Diagonal, maybe rotated as well. These are all control panel. Control panel. So this is how a resistive heating process or thermal evaporation looks like. So this is a tungsten board. You're going to see later on the next slide. Tungsten board. Tungsten board. Where you put in your precursor material like aluminum wires or silver or whatever. So turn on the current high enough that you will see the color starts to change to orange. Does that mean the heating is taking place in the boat? So you're gonna have your sample normally in the center. So the sample is gonna be melted, it's gonna form liquid aluminium, and then it's gonna start to change to gas phase. It's gonna be evaporated. So your wafer is gonna be somewhere here, up there. Kalau ni chamber, if you can imagine this is chamber. So it needs to travel from there to there. So this is your silicon. So it's gonna be transported, or it's gonna be evaporated and then condensed on your silicon up here. So you're gonna have your aluminium on silicon eventually, right? So that's called resistive heating. Kita kena kepit dia. Kalau you pernah buat evaporation, you have to like screw dia lah, screw so that it's tight enough and the current can pass through the tungsten board while you actually increasing the current during the process. Right, it's a simple, robust, widespread use, can only achieve temperature up to 1,800 degrees C, and this is in fact high enough. Well, typically we do at up to 1,000 degrees C. You can use tungsten, tantalum, molybdenum filament to heat evaporation source. So this is actually the boat. So the filament here is the boat that we saw, the orange ones now. So filament or the board can handle up to 200 to 300 amperes of current. This is very high. Typically, we don't go up to this level. So exposes substrate to visible and IR radiation during the evaporation process. So you can see the color, right? So it's visible and a bit of IR as well, some heat. So typical deposition rate is 1 to 20 angstrom per second. So that's like 0.1 to 2 nanometer if you want to convert into nanometer. But it's not always true, because the system that I use, but my system when I did a PhD was on electron beam evaporation. The system evaporation, the deposition rate can go up to 1 micron per minute. 1 micron per minute. So kalau you convert per second berapa? 1 micron per 60 second, right? 1 micron per 60 second. Saya calculate. 1 micron bahagi 60 second. So that's like 0.016 micron times 1000. So 16 nanometer per second, right? Slightly higher than this. 17 nanometer per second. So that's considered high. Even though you have a system like 500 nanometer per minute, it's considered high already. And if you compare low depth rate and high depth rate system, other certain issues. On the low side, you normally have better uniformity, but the process is slower. If you go to the high side, that means increase up to say 1 micron per minute deposition, the uniformity tends not to be so good, but then you have a faster throughput for your mass production. So it's a trade-off between what you want and your application. Common evaporate material or your sources can be, well, typical metals, gold, silver, and whatnot. And you can also evaporate magnesium fluoride, calcium fluoride, lead sulfide, lead selenide, and stuff like that. So these are among the examples of your tungsten boat. Right, boats can come in many shapes. The typical one that we have in our lab is like this. In our lab, it's based on tungsten boat. You can also use other high temperature material like tantalum, molybdenum that won't be melted easily. Kalau tidak, dia akan melt sekali dengan you punya material, so no point. So pass high current through such boats and then heat them due to Joule heating. Resistive heating is also called Joule heating. Sama, if some people mention Joule heating, then it's actually resistive heating ataupun thermal evaporation process. So metal placed in the boat melts and evaporates, and single atoms, it's not single, multiple atoms, fly to the target in high vacuum environment. So your sources is something like this. You may have few sources. Okay, you may have few sources like this. So not necessarily a single source. So ini dia punya illustration sama. The boats can come in many shapes and sizes and materials as well. So kita tengok sekejap lah. Then we finish the Sorry, can you see the YouTube page? Or I still need to reshare? Can you see? No, okay, all right, it's okay. Let me share the page. Yeah. Saya akan, I'm not going to show you the whole video. I'm just going to go through a few phases and then you try to see. I'll explain as it goes. Right, now can you see the YouTube page? Okay, good. Right, so this is close to what we have in NOLAB. Kalau tengok dalam bilik sputtering tu. So it's on the far end facing TI, school TI. Yeah, you're not hearing you don't hear the voice, right? No audio, just video, right? No. Okay, no voice, that's fine. Okay, kita punya panel something like this as well. It's an old system. I think it's back in the 90s, so it's been running for like 30 plus years. So, okay, we have a control panel here. It's a very old school system. Even your card here, you can see my arrow, right? Can you see my arrow on the page? I'm pointing now on the knob. Okay, good. So you can see the arrow. So this is a knob for you to increase the current. Nanti you tengok sendiri lah, dia punya full video dekat link YouTube tu. So this is the ampere level. So if you increase the knobs, then you'll see the current increases. So you might need different levels of current for different materials. So this is the voltage control. So basically this is a all control panel for you to do deposition. So this is inside the chamber. So you don't place the chamber yet. This is inside. So down here is you can see there is the tungsten board where you place your prism material, for example, aluminium. So that is the mechanical shutter. So over there, up here is the crystal monitor. We don't have it in our lab. So it will monitor the deposition rate the moment you start on the deposition process. So it tell you like a couple of nanometer per second and stuff like that. So this is perhaps your aluminium, aluminium that you've cut from the wires. So you put it there, and then you screw it in so that it's tight enough for the current to pass through later on. Kalau you tak tight enough, then kalau dia longgar, for example, if you dah vacuum sampai time -5, and you turn on the current, you see nothing is happening on the board. You don't see any orange color. So that is a bad sign because it's a sign that your connection is not tight enough. So here you dah vacuum from atmospheric pressure down to -5 for like half an hour, 1 hour, and then suddenly no current pass through, and you wasted like 1 hour, and then you need to vent again just to make sure that you retighten and the connection is proper. So I had a couple of experiences last time when I did my MSc in NOLAB. So I forgot to do it tightly, and then I wasted like 1-2 hours. I got nothing out of it. Saya cepatkan sikit video ni. So now, okay, they use transparent bell jar, but in our lab we use opaque chamber yang tak nampak, but we have a glass window. This one is slightly easier because you can see the whole thing, but then you are more exposed to the radiation in that sense, right? Because it's transparent in nature. So now what he's trying to do is he's trying to vacuum the chamber. So he's pumping down. So the system is going to display the current pressure. So let me just go slightly faster. So well, you can see that the chamber is now sealed. So you can start the vacuuming process. So now it's going down to -1. You see, it's using roughing pump yang saya tunjuk dekat awal-awal slide dulu, which will take the pressure from atmospheric down to about -3, and then it starts to kick the fine pumping. Well, now we use diffusion pump to take the pressure further from -3 to about -5, -6 before you start the deposition. So now I think it's almost ready for the deposition. So he turns on the current. So at 2 ampere, I think. So now increases further, and let's see what happens in the next 1 minute or so. We tengok what happens at the tungsten board there as the current is increased. The shutter is still on the board, maksudnya tak ada deposition on the substrate yet. So you start to experience current is now passing through the board, and you have your melting takes place. So now you remove your shutter, evaporation starts, and then you have a deposition straight on the substrate. Then your deposition finish, you close the shutter, you block balik sebab you tak nak ada still ada deposition sebab current is still there, so you might evaporate still some of the materials. Then reduce the current to 0, and then you vent the chamber from -5 back to the atmospheric level. So it's going up slowly. So now it's now at atmospheric pressure. You can remove the chamber and remove your sample for the next process. There you go. So you have a deposition of whatever, perhaps aluminium. See the sample, the glass slide that is not deposited on the left and deposited with silver on the right. So you can see the color difference. So this is how it looks like after the evaporation process. You normally have a residue of your material on the board. You can reuse for the next time. We normally control like maybe 2 times, 3 times, and after that you will see the board is usually is a bit brittle. It's a bit brittle. The more deposition that you do on the board using the board, dia akan jadi lebih brittle because it has gone through like a couple of evaporation processes. So dia akan jadi brittle, dan kalau you pegang well, if you exert a little bit of extra pressure, they can just break. Then it's time to change to a new tungsten board. Okay, let me see what else is left on the slide. I'll just continue next time. So we're now on page, hold on. We're now on page 21. So yeah, so the next one will cover electron beam evaporation, and then we'll move on to sputtering and all the process parameters related to both deposition techniques, right? So done with thermal evaporation. So is it okay so far? Can you understand how thermal evaporation looks like? Can you follow? Paham ke? Tak paham ke? I need to know, is it okay or not? Okay, all right. All right, it's good. So we're gonna have like 2 parts for film deposition, PVD and CVD. Then next topic we're gonna go through, yes, easier than diffusion. That's good. All right, easier than diffusion. Yes, evaporation is one of the simplest technique. If you talk about wafer fab, normally kalau dekat Citera, we have TFM and TFD, thin film metal and thin film dielectric, 2 different departments. So satu department tu buat metal saja, metal deposition like tungsten, aluminium, silver, and copper and whatnot. And the other department, TFD, does dielectric deposition, silicon nitride, silicon oxide, silicon carbide, and whatnot, right? So it's a rather simple process if you compare to lithography, etching, diffusion. Okay, so it's quite stable if you compare to others. So tak banyak issue sangat lah. If you're a PE process engineer for this particular process, then I think your life will not be so complicated if we compare to litho and etch. All right. Okay, so we'll continue Thursday then. No questions for today. Bye-bye. Take care. Assalamualaikum.